How do we differentiate our exponentials? The method we came up with yesterday is okay, but that's annoying, having to work out the slope at x equals 0 every single time. There must be a better way of doing it. So we'll just start with base e. So e is going to be to the power of some function of x, could be anything. So I'll just let u equal that function of x. So now I'm just differentiating y equals e to the u, and what we saw yesterday was that's the simplest derivative we could have. When it was y equals e to the x, the derivative was e to the x. So if I differentiate this with respect to x, well, I can't do it with respect to x, it's u. So I'll use my implicit differentiation idea. I'll differentiate it with respect to u and then multiply it by du dx. Well, differentiate e to the u with respect to u is e to the u. That's what we saw yesterday, world's easiest derivative. Times du dx, which is the derivative of u with respect to x, which is f dash x. If I sub back in for u, I now have a formula that allows me to differentiate any exponential to any power. All I've got to do is differentiate the power and put it out the front. And this is where we've got to be careful, because with polynomials, you remember, we take one off the power. We don't do that with exponentials. The power always stays the same. So if y equals e to some function, all I do is differentiate that function, whatever the power is, that goes to the front, and e to the function x power does not change. That's great if it's the natural base, e, Euler's number. If it's some other base, what do we do? Well, it's exactly the same with one slight addition. We also then multiply it by the log of a. And this all comes down to the change of base formula that we saw in logs. That's where it comes from. Basically, we're changing the base. I know how to differentiate when the base is e, so if I change the base to e, I could do it. And that's where this derivative formula comes from, basically. Alright, let's just do something. Yeah, we hope they give us this one. The world's easiest derivative, y equals e to the x. Derivative is e to the x. But if it's some other power, we have 5x. Well, what we now know is all I've got to do is differentiate the power itself. If I differentiate 5x, I get 5. So we'll get 5 e to the 5x. 4x plus 3. Differentiate 4x plus 3, I get 4. So it's 4 e to the power of 4x plus 3. It doesn't have to be a linear function. I've got a quadratic this time. Differentiate that quadratic, we get 2x plus 3. So it becomes 2x plus 3 times e to the x squared plus 3x plus 2. The power does not change. And now if I've got this sort of question, find the tangent to this curve, y equals e to the 2x plus 1, at the point 1, and the exact value for the y would be e squared plus 1. Well, it's no different to the ones we saw before. Tangent is a line. I need two things. I need a point, I need a slope. I've got a point. I need to find the slope. Slope of a tangent, that's where we used calculus. So y equals e to the power of 2x plus 1, differentiate that, we'll get 2e to the 2x. There's the formula that'll allow me to find the slope. We'll sub in x equals 1, that's the point we're interested in. dy dx becomes 2e squared, point slope formula. So y minus the y value, which is e squared plus 1, is equal to the slope, 2e squared, times x minus the x value, which is 1. It's a strange looking thing, but that's because we're using irrational numbers there. Remember, e is just a number. We don't know what it is exactly. So we end up in general form, 2e squared x minus y minus e squared plus 1 would be 0. That would be the exact value of the equation of the tangent. Alright, well here's one where the base is not e. What we said was it's no different. I'll do it exactly the same. Differentiate the power, differentiate x squared, I get 2x. So it becomes 2x, but I have that additional thing in there now. I also need to multiply it by the log of 4. Log of 4, and then times 4 to the power of x squared. And by the way, if you see the word log with no base written, we assume the base is e. So the natural base. Speaking of the natural base, so the natural logarithm. That's the logarithm that is base e, Euler's number. That's what we call the natural logarithm. So if y equals e to the power of x, they're inverses, therefore x will be the natural log of y. In this case, I have written the base down. Sometimes you'll see it this way, ln. Makes it obvious we're talking about the natural log when it's written as ln, and that's why it's labelled that way on your calculator. You'll see it as ln. Why ln? Comes from the French, where they wouldn't say natural logarithm. Who did French? They have this weird way of putting words the other way around. So they wouldn't say natural logarithm, they'd say logarithm natural. So that's why it's ln. And as I say, if you just see log without a base written down, we would assume they're talking about the natural logarithm. Simplify then the log of 1 on e. All the log laws are still the same, so if I rewrite that, I can write it as the log of e to the power of -1. The negative I can bring to the front, but the natural log of e, they're the same base. They will cancel. Log e was 1. So -1 is the answer. E to the power of 2 log 3. Well, before I can cancel in this case, because the base will cancel with the log, I need to get the 2 inside the log. So I use my log law, it becomes e to the power of log 3 squared. So that's 3 squared, 9. Still all the same rules that we saw with ordinary logarithms. Okay, so 11c, 11d, and 11e as well.